So in 5.6, we're going to talk about graphing polynomial functions. And again, just like we have in really a lot of this polynomial unit, we're going to have some things that are review. So the first thing I've got up here that's review, but important to know, is that fundamental theorem of algebra, that a polynomial of degree n has at most n unique roots. So that means degree 4, most is 4 unique roots. Now remember that if we have roots that appear more than once, that those get counted in that degree, which we'll talk about more in our example. What we haven't learned yet is the corollary to that fundamental theorem of algebra, and that is that a polynomial of degree n has at most n minus 1 extreme values. Extreme values are sometimes called relative extrema, which means relative minimums and maximums, which we've talked about relative min and maxes before. Remember that a relative min is the bottom of any valley. So like right here would be a relative minimum on this quartic graph. A relative maximum is just the top of any hill. Doesn't have to be the highest hill, so it could be this guy down here, but it has to be the top of a hill. I've actually taken the same chart that we had in our 5.2 notes, and I just copied what we had filled in there about n behavior, because n behavior is going to come back with these graphs. So I've already got some n behavior descriptions in words. So it says low and high. It could be goes down, goes up. Those mean the same thing. But what we haven't talked about is arrow notation, and that's going to be in this quiz. And arrow notation always takes this same format. The only thing that we are gonna have to change each time are these blanks. And we either put an infinity in here if it's supposed to go up, or a negative infinity if it's supposed to go down. And that's going to be the same thing on the second line as well. Now, what this means, as x approaches negative infinity, what that's saying in math speak is on the left side. Then, after the comma, we say f of x approaches, that's what the arrow means, approaches, either infinity or negative infinity. So what that means is f of x are the y values. It's saying the graph goes blank. So if it goes up, we put infinity. If it goes down, we put negative infinity. This second line, and these are both part of the n behavior. You have to have both every single time. This says, as x approaches infinity, says on the right side. And then this part is the same, just says the graph goes, and then we fill in the blank there. So that's what arrow notation is. We also have to worry about in this section when we're talking about polynomial graphs is the behavior of the x-intercepts, because being able to connect an equation or a set of roots to the graph requires that you know this behavior. And that is that real roots, so not imaginaries, imaginaries we can't see on a graph anyway, but real roots with odd multiplicity. Odd multiplicity means exponents. So real roots that have an odd exponent, so an exponent of 1, an exponent of 3, 5, so on and so forth, those cross the x-axis. So when you see it, it does something like this. It goes across. Or could be on the other side, something like this. Real roots with even multiplicity, meaning that the exponent on that particular factor is 2, 4, 6, so on and so forth, touch the x-axis and turn back around, which means that if this is the root, it looks like this, or could maybe look something like this, meaning that it creates a relative maximum or a relative minimum at that particular x-intercept. So it's important that we know that behavior. So we're going to look at an example for a polynomial here and just go through a whole bunch of questions. So in A, how many roots does f of x have? Now, I wrote this one here because I don't want you to get tricked. It has at most n unique roots, which if we look at this, this is a plane x, this is an x squared, this is an x. So I have an x times an x squared times an x, which these are both x to the first. When we multiply, we add exponents. We know that this would create, if we multiplied it out and put it in standard form, it would create a quartic, an x to the fourth. So that means it can have up to 4. So at most, it could have 4. But because we have the actual equation, we can actually figure out how many it has. So we can find its x-intercepts by setting each of the factors equal to 0. X plus 2 equals 0. X minus 1 equals 0. Notice that that's a squared, which means it happens twice. It's a double root. And then x minus 4 equals 0. So that gives us x equals negative 2, x equals 1, x equals 4. This x equals 1 is not unique because it happens twice. So we get 2 x equals 1s essentially. But when we're saying how many roots does it have, there are just 3 unique roots. Because we would count that x equals 1 twice, that's how we make the degree equal the number of roots. But it just asks how many. It doesn't want you to count them twice. So in this case, there are only actually 3. All right, what is the maximum number of extreme values? So we already said that this is degree 4. And so this does say the maximum number. It doesn't say how many does it have. It says it's the maximum number. And so if n equals 4, then n minus 1 equals 3. So 3 extreme values would be my answer there because of this corollary. So degree n, max is n minus 1 extreme values, so 3. C, describe the end behavior of f of x in words. So knowing what's going to happen. So I'm going to show you 2 different ways to do this. One is by looking at the equation. So we've already talked about what, if we put it in standard form, that I would have an x times an x squared times an x. And notice that there's no numbers in front of these x's. So this would, 1x to the fourth would be my leading term, which means that this has a positive leading coefficient because it's 1x to the fourth, and it's quartic. So a positive quartic is going to start high and end high, which means that in words we can say both ends go up, is what they would want us to say there. Describe the end behavior in arrow notation is where this comes in. And again, what's typed out in the text, we never change. So I say as x approaches negative infinity, f of x approaches, and I'll leave that blank for now, as x approaches infinity, f of x approaches blank. So we just said, based on the fact that I know this would be 1x to the fourth, that it would end up being this situation, both ends up. That means that these blanks, since both ends are supposed to go up, should both be an infinity. And this would be my end behavior. So this one, I want you to know that if it starts low, that means that this one with a low end here and a high end here, this is saying as x approaches negative infinity, f of x approaches negative infinity because the left side is down. This side, as x approaches infinity, the right side of the graph, f of x approaches infinity. So here they go opposite directions. Left side is going down, right side is going up. This quadratic is going to have the exact same end behavior as this quartic because both ends are going up. This cubic, exact same end behavior as this linear. And then obviously we have some changes down here where here we would have negative infinities on both sides. So negative infinity in both blanks. This one, same thing, negative infinity in both blanks. This one, as x approaches negative infinity, so on the left side of the graph, f of x approaches infinity because it goes up on the left side. And as x approaches infinity, f of x approaches negative infinity. So right side going down. This guy, same end behavior as this guy. So you can see some patterns that develop there. So next thing we want to do is we want to create a sketch of f of x. So this is just going to be a rough sketch because obviously you can graph it, but I want you to understand how we make the connections between the actual equation and the graph. And if I just graph it right away, you really won't understand those connections. So first thing I know is that both ends have to go up. So when I'm done drawing all my roots, all my x-intercepts, I need both the ends to go up. So I know that my roots are at x equals -2, so that's an x-intercept. X equals 1 right here, and x equals 4. So these are my x-intercepts. I know that there aren't any more because this is a double root. And remember, you can't have just one imaginary. Degree 4, 4 solutions. This guy is the double. You can't have an imaginary because they always come in pairs. So I know from the end behavior that both ends go up. So after the last on each side, I make it go up. I also know, based on my x-intercept behavior, that x minus 1 has multiplicity 2. It's even multiplicity. So that means that at x equals 1, I need it to turn around. And the other two, because they're both to the first power, those are odd multiplicity. So this is going to cross the axis. This guy, I need it to touch and then turn back around. And then I know this guy has to cross, so I have to come back up. So this is, in general, what my graph has to look like based on all those things. Last one is to give an approximation of a relative minimum of f of x. Now this one, they would give you the graph most likely. So here, if I go to Desmos, and you can see I've got that equation graphed over here. So x plus 2 times x minus 1 squared times x minus 4. And I can see that indeed I have kind of a similar shape to what I had before. If I zoom in, because I'm trying to get an approximation here, I have to zoom out just a little, because I can see that it's a little bit below -20. And this would be -20.5. So I might say -20.25 is the y coordinate. The x coordinate, we're counting by ones here, and it looks like it might be just a little bit past. I wouldn't even say a quarter. So my approximation there might be like -1.1. So that's a relative minimum, -1.1, and this is an approximation, -20.25, so 0.25-ish. Now, that's a relative minimum, bottom of a valley. It's not the only one. There's also a relative minimum over here, which looks like it's just past 4. So I would maybe say approximately 4.1, negative 20.25. Now this didn't ask us for a relative max, but if we did, the only relative max on this graph, the only top of the hill, occurs at that x-intercept. So that one we wouldn't have to approximate, we would actually know that that's at 1, 0. All right, so that should give you a pretty good idea of what to do on the quiz. Make sure that you ask if you have questions.